Hello again, this is Matthew Van Prague, and today we are reviewing Chapter 2, Sections 2.7 to 2.12 for regression analysis. Specifically, this chapter expanded on the topics introduced in last week's discussion about the usefulness of regression analysis and introduction of topics such as correlation coefficients and parameterizations. For this week, we will start by specifically focusing on the regression parameters and determine confidence intervals to display just how confident we are in these estimates. To start, we should assume that the epsilons in this equation present a normal distribution, since this will allow us to conclude that beta hat sub 0 and beta hat sub 1 are also normal. From here, we can display a confidence interval for beta hat sub 0, as demonstrated by this formula shown here. We can see that each portion of this equation can be taken out and explained, like the t sub n minus 2 comma alpha over 2, which is the 1 minus alpha over 2 percentile of a t distribution. This helps us construct a meaningful t-distribution for beta sub 0, and demonstrates to us just where the point may lie. The same is true for beta sub 1, which can be constructed using the same formula, except with beta hat sub 1 in place of the prior beta hat sub 0. Now, how is this useful to us? Well, if we were to take multiple samples at the same values of x, and create a 95% confidence interval for each particular sample, then 95% of these intervals would demonstrate the true value of the slope. 95% is a particularly important value for us because it relates back to the 95% normal distribution within 2 standard deviations of the mean that is so integral to basic statistical analysis. To see this equation in action, the textbook uses Table 2.9 as a quintessential example. We take the coefficient, add or subtract the t sub n minus 2, a over 2 percentile, and multiply the standard error, which gives us the confidence intervals for our equations. This can give us a useful range where the answer could fall between. The problem was talking about wait times, so these numbers would express that a wait time would typically be between 14 and 17 minutes. 95% of the time this would happen. Now, an interesting feature of this equation is the graphic scheme of these confidence intervals would not be rectangular, like some people would expect. Instead, the confidence region for beta sub 0 and beta sub 1 would be elliptical, a special case for regression, and this means the possible data values that fit inside these endpoints is smaller than one might anticipate. Last week, we discussed the usability of correlation coefficients versus regression analysis, and detailed how the former couldn't predict future points, and yet the latter can be used to take past data and create informed predictions about upcoming data. And Section 2.8 tells us how to do this, notably using what is referred to as the fitted regression equation. Firstly, we should understand there are 2 separate types of predictions. The first of these predicts the value of response variable y based on our prior predictor variable x sub 0. As we've mentioned in the last class, regression analysis focuses in on y as our primary variable and sublimates x as an auxiliary variable of sorts, solely meant to determine our eventual y values. The second method of prediction, however, deals with the estimation of the mean response mu sub 0, in the special case where x equals x sub 0. Now, each of these predictions are useful in different cases, depending on whether you want the less accurate but exact data points, or a better predicted range of data points, with each equation relating to the respective wishes of the user. Now, both of these predictions are related to these equations, the prediction of response variable y on the left, and the estimation of the mean response mu sub 0 on the right. What you'll notice is these equations are largely similar, except in 2 key distinguishing features. you'll see that the point estimate, aka the first line in each example, is identical, yet the standard error is quite different. For the response variable y case, we see an additional 1 at the start of what's under the square root, and this is absent in the mu sub 0 case. This goes back to the uncertainty of homing in on a specific future data point, which is what y ventures to do, but mu sub 0 is only looking for a good estimate of future data points, meaning there is less uncertainty, therefore no reason for an additional 1 at the beginning of the square root. As for the last row, while they look similar aside from separate variables, they have different meanings and names. The confidence coefficient for y is referred to as the prediction limit, while the coefficient for mu sub 0 is the confidence limit, which reflects quite nicely on each of their purposes. To see these differences in action, let's bring back the wait time example and show the standard error when we predict a specific y value. In contrast, here is the standard error in predicting a specific mu value. One can plainly see the value on the right is substantially lower than the value on the left, because we have lower variability for the mu example, and therefore, we are more certain about our estimates. Now, as is customary, the standard error of prediction increases the farther the predictor variable is from the actual observations, meaning incredible outliers from your regular data will yield incredibly significant results. In these cases, you should adjust your equations to fit these strange data points, and always take care in the values you utilize. Remember, everyone, we are not only interested in seeing whether or not a linear relationship exists, or how strong this relationship is, which was what was detailed in our previous discussions, but we are also interested in the correctness of the fit of the model to the data. 4 main ways exist to determine the quality of this fit. Firstly, we have the case where the null hypothesis is rejected. Here, the extremity of the values describe to us the strength of the linear relationship between y and x. By finding a large value for t, or a small corresponding p-value, we have a strong linear relationship, and the same is true for the inverse. Secondly, we can ascertain the relationship by directly observing the scatterplot of the 2 variables. Like case 1, there is a clear-cut way to simply notice a strong linear relationship, notably if the data points from a somewhat straight line. This isn't a foolproof method, but it does only require simple observation. The third case is to examine the scatterplot between y and y hat. Like case 2, we can observe a straight relationship, but we need a specific equation to compute the straightness of this line. This equation can be observed here by the correlation coefficient, where y bar represents the mean of the response variable y, and y bar is the mean of the fitted values. Notably, this graph and the graph of y versus x are identical, which means that this associated equation is therefore true. However, the correlation coefficient of y comma y hat cannot be negative, while y comma x can be. This means, in simple linear regression, which we are currently studying, these 2 expressions mean the same thing. But when we expand to multiple linear regression, their meanings will be different. Finally, the 4th case, there is a useful way to compute the least squares estimates of the parameters of a linear model. These values for SST, SSR, and SSE will prove especially useful for this case. SST, first of all, represents the total sum of squared deviations in y from mean y bar. SSR represents the sum of squares due to regression. And lastly, SSE represents the sum of squared residuals. These three are related by the equation SST equals SSR plus SSE. To get a better visualization of what these values mean precisely, we can reformat the equation to y sub I equals y hat sub I plus the difference between y sub I and y hat sub I. This equates to the observed quantity equaling the fit value added to the deviation from the fit value. If we subtract y bar from both sides, however, we see that we can re-express this equation as the deviation from the mean equaling the deviation due to fit added to the residual. This method of reformatting allows us to interpret these numbers in all sorts of useful ways, including with the ratio r squared. Since r squared represents the ratio SSR divided by SST, we can also rewrite this as 1 minus SSE divided by SST. Now, we've introduced r squared to the equation, but we must understand that this r squared is equal to the square of the correlation coefficient between y and x, or between y and y hat. We also refer to r squared as the goodness of fit index, and this can measure the total variability in y as a result of predictor variable x. R squared exists on the range between 0 and 1, and if r squared is closer to the maximum, then x will account for a majority of the variation in y. Because of this, r squared is also referred to as the coefficient of determination, since it determines the response variable y quite efficiently. Here is the computer repair data from earlier expressed in these terms, revealing a quite high goodness of fit index. This value of 987 thousandths reveals a 99% of the total variability in y that is accounted for by x. Now that's quite high. This, in turn, represents a strong linear relationship. As a cautionary reminder, however, the regression assumptions should be checked before drawing statistical conclusions from the analysis, because the validity of these statistics hinges on the validity of the assumptions. If you have faulty assumptions, then this will not work, and you should correct the equations to fit. We have previously considered fitting the model y equals beta sub 0 plus beta sub 1 multiplied by x plus epsilon. However, we must also account for the example without an intercept, or y equals beta sub 1 multiplied by x plus epsilon. This second model is known as a no-intercept model, and this may have to be used in occasions where the line does not pass through the origin. Since beta sub 1 is a new value that is now expressed on its own, we must demonstrate the equations relating to this variable. The least squares estimate of beta sub 1 would be represented as the summation of the product of y sub I and x sub I divided by the summation of x sub I exponent 2, with the ith fitted value of y hat sub I being represented by the product of beta hat sub 1 and x sub I. Also expressed here is the corresponding residual, with equation E sub I equals y sub I minus y hat sub I, and the standard error of b hat sub 1 being represented by sigma hat over the square root of summation x sub I exponent 2. Not all models with an intercept will work under this model designated for no intercept, notably the r squared we just suggested earlier. If we want to do the opposite, however, and fit the equation for a model with an intercept, into an example without an intercept, we can just replace this equation's y bar with 0. Here, r squared can be the proportion of the variation in y from x after adjusting y by its mean. Now, the choice between equations with an intercept and without an intercept isn't always crystal clear, and so we should be careful to select one of these two. We can select one of these equations by comparing the residual mean squares, since this equation is meant to measure the proximity of the predicted values from the observed points. We can also use a t-test to test which model, and if the test is significant, the intercept equation should be used. Otherwise, the no intercepts method is preferable. Lastly, we have two examples of regression models which do not contain regression coefficients. Let's look at them one by one. The first of these emerges when we want to test for mean mu of a variable y based on a random sample of n observations. The null hypothesis is that mu equals 0, and the alternative hypothesis is that mu doesn't equal 0. However, here we see two models that reveal separate results. In case 1, mu equals 0, but in case 2, mu does not equal 0. And this is plainly contradictory. How can something equal one thing, but not equal that one thing at the same time? By comparing the t-tests to one another, we see this model, which is the same as the one sample t-test in this example here. Now, in our second example of a trivial regression model, we have a paired two-sample t-test. The textbook uses the example of whether a diet is conducive to weight loss, and a random sample of n people is chosen to follow this diet for a predetermined period of time. We let y equal y sub 1 minus y sub 2 represent the difference between two weights. Y would be a random variable with mean mu and variance sigma squared. Testing the effectiveness of the diet is akin to testing a null hypothesis where mu equals 0 and the alternative hypothesis is mu being greater than 0. This turns into a model similar to our last case, where both of these outcomes can be reached, and therefore the result is inconclusive as to whether or not the diet was effective or not. And now for the summary. To sum everything up, we started by establishing what a confidence interval is, its importance to the overall equation, and ascertained formulas of how to obtain it. Afterwards, we found out how to predict future points with the fitted regression equation under two criteria: the response variable y against x and the estimation of mu sub 0 against x, in which the latter is much more certain, considering it develops a range of answers rather than just one particular answer. Moving forward, we found the importance of measuring the quality of fit, specifically under 4 cases, using t-values, scatter plots, and correlation coefficients to find the strength of the linear relationship. This is where concepts like SST, SSR, SSE, and R squared were introduced as important aspects of the measurements between y and x. Afterwards, we differentiated between regression lines that pass through the origin and those that don't, while also finding how to see when each equation is preferable, and seeing if these two can reverse. Lastly, we observed 2 specific trivial regression models that do not follow this procedure, and these models are possible in both one sample and paired two-sample tests as special cases of simple regression analysis. Moving forward, we saw many cases today that have different values in multiple regression analysis, and we will see these in upcoming chapters. Moving forward. This has been an outline of Chapter 2, Sections 7 through 12. Thank you for watching, and have a good day.